Geometric sequences and series. A geometric sequence is a sequence in which each term after the first is obtained by multiplying the preceding term by a fixed non-zero constant, the common ratio. So basically, instead of adding a common difference like the arithmetic sequence did, this sequence has a multiplier. So it almost works like an exponential sequence. In fact, it pretty much does. So let's say, for instance, that I had the sequence 1, 5, 25, 125, 625, so on and so forth. The common ratio, which we use R for, would be 5, because you're multiplying by 5 each time. 4, 8, 16, 32. R is 2. 6, negative 12, 24, negative 48, 96. That one, their common ratio is negative 2. And of course, things can get smaller as well. For instance, if I had 9, negative 3, 1, negative 1/3, then the ratio would be negative 1/3. And if you were to plot these, you'd get a discrete graph again. But basically, you would end up with something that either goes upward like this exponentially, or it comes downward exponentially like that. So you can kind of see that kind of curvature that you would with an exponential function. Like if I were to try to superimpose an exponential function on this, remember, don't write anything I write in yellow because that's the magic pen. It's just stuff I'm showing you because I can't point at it. So there are the two exponential curves that kind of get traced out by those dots. Now, for example, write the first 4 terms of the geometric sequence with first term, we'll call it A1, 6, and the common ratio 1/3. Oh, did I say 4? I meant 6. We're supposed to have 6 terms here. We'll make that into a 6. Ha ha ha. Here we go. Anyway, A1 is 6. A2 would be 6 times the common ratio, which is 1/3. 1/3 of 6 is 2. A3, if I take 2 times 1/3, that's 2/3. A4 would be 1/3 times that, which would be 2/9. A5 would be 1/3 times that, which would be 2/27. And then A6 would be 1/3 times that, which would be 2/81. Well, let's talk about recursive versus explicit formulas for these. So if I wanted a recursive formula, if I want to get A sub n, I could take R times the term that came before it. Now, consider this. If I start off with A1, then the next term, A2, would be A1 times R. And the next term, A3, would be A1 times R times R. And A4 would be A1 times R times R times R, because I'm taking the previous term and multiplying it by another R. So, if you continue that pattern, if I want the nth term, I could take the first term and multiply it by r to the n minus 1th. And that's the explicit formula. For a geometric sequence. All right. So let's say we wanted to do something with that. Let's say find the 8th term of a geometric sequence whose first term is -4 and the common ratio is -2. Well, I know that the nth term of this sequence would be the first term times the common ratio to the n minus 1st term, or n minus 1st power, rather. So, if I want to find A8, that would be -4 times -2 to the 8 minus 1th, which would be the 7th. Well, -2 to the 7th power would be -128. Times -4 would be 512. Okay. Now, one place where this is useful is population growth. If you remember back to college algebra, we usually did population growth with a formula that looked like this. The population is the initial population times e to some kt. Well, from the perspective of a geometric sequence, basically what you can do is you could take a data table, which would have several different years worth of population data. You can use it to find the common difference, and then you can use it, or not the common difference, the common ratio, and then you could use it to generate different year of population growth. So for instance, here's the US population. So the year 2000, so this would be years, and this would be population in millions. So in the year 2000, the population of the United States was 281.4. You know what? I'm going to pause this while I write this data table. Bam! Anyway, so you've got this data table, right? I don't even care if you write this down or not, really, but there it is. So the first thing is show that this is increasing geometrically. Well, basically, all you would have to show is that there's a common ratio. So if you take any two consecutive years and divide them, you get the same number. So for instance, 284.5 divided by 281.4 happens to come out to be roughly 1.011. And if you take any two more that are consecutive and divide them, it comes out to be roughly the same. So then it says, write the general term for the geometric sequence in n years after 1999. Well, so basically, what you would have is you would have to have you'd have an equals a1 times r to the n minus 1. Well, your r is this right here, and that's your a1 right there. So basically, all you'd have to have is an equals 281.4 times 1.011 to the n minus 1st. And then it says project the US population in millions for the year 2009. Well, 2009 is 10 years after 1999. So basically, you would have to have A10 equals 281.4 times 1.011 to the 9th power, which would come out to be approximately 310.5. And that would, of course, be in millions of people. All right. Now, Let's talk about the nth partial sum. Wow, I can't spell. Fail. So, we'll call it S sub n. So I'd have the first term, plus the second term, plus the third term, plus the fourth term, plus all the way up to the last term in this particular partial sum. Now what I'd like to do is I'd like to take r times S sub n. So that would be a1r plus a1r squared plus a1r cubed plus a1r to the fourth plus dot 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 plus a1r to the nth. And what I'd like to do is I'd like to subtract those two. So basically we're going to subtract these. Well, so I'd have S sub n minus r times S sub n. Well, I'd have a1, but then notice that this term and this term are the same, and I'm subtracting. And then this term and this term are the same, and I'm subtracting. And then this term and this term are the same. And so on and so forth. Basically, everything's going to cancel out except this last one here. And since I'm subtracting, got interrupted briefly right there. I don't remember what I was saying, but anyway, this is minus a1 r to the nth, because that's the only piece that doesn't cancel out. So what we can do is we can factor out S sub n. So this would be S sub n times 1 minus r, and we can factor out a1. This is 1 minus r to the nth. And then if we just subtract, we get the following formula. So the nth partial sum is equal to a1 times 1 minus r to the nth power over 1 minus r. So that's a pretty useful formula. Let's find the sum of the first 18 terms. So if it's the sum of the first 18 terms, I want to find S18 of 2, negative 8, 32, negative 128, etc. So notice that I can find the common ratio. The thing you're multiplying by every time is negative 4. And of course, A1 is 2. So if I want to find S18, I'm going to take A1, which is 2, times 1 minus negative 4 to the 18th power over 1 minus negative 4. Now, negative 4 to the 18th power is a pretty big positive number, and 1 minus that would be a pretty big negative number, times 2 divided by 5. Well, anyway, that, according to my calculations, comes out to be negative 27,487,694. That's a fairly large number. Now, in the last minute, let's see if we can also calculate this. The sum from I equals 1 to 10 of 6 times 2 to the I power. Well, notice the first time this would be 6 times 2 plus 6 times 2 squared plus dot dot dot, right? Plus 6 times 2 to the 10th. So basically I'm finding S10 where A1 is 12 and R is 2. So S10 here would be 12 times 1 minus 2 to the 10th over 1 minus 2, which would apparently give us 12,276 if you crunch the numbers.